Okay, single replacement reactions. Single replacement reactions are another class of oxidation reduction processes whereby an active metal will replace a less active metal, or a more active halogen will replace a less active halogen in a ionic compound. Generally, A plus Bx goes to Ax plus B will represent the single replacement where A replaces B. A is a more active element than B and generates another salt in terms of A, and B returns to basic standard state. The way you decide which element replaces which element is through the activity series. So this is based upon activity series. Which, as you see here, starts with the more active lithium, potassium, calcium, sodium, and proceeds through less active down through gold in this list. Halogens start with chlorine, then go to less active fluorine, bromine, and iodine. As an example, we're going to start with the molecular equation. Let's use zinc in basic standard state reacting with a copper sulfate in aqueous solution. Now we find zinc is here on the activity series and copper is here on the activity series. Since zinc is more active than copper, then zinc will replace copper, and copper will be converted to basic standard state. So the outcome is zinc sulfate aqueous plus copper again and basic standard state. Now this can be written in an ionic equation in the following way. By showing the copper sulfate being aqueous in ionic form on the reactant side and zinc sulfate in aqueous solution in ionic form on the product side. So let's see, we take zinc in basic standard state plus copper 2 to be exact, because it neutralizes with sulfate. That'll be an aqueous ion plus the sulfate ion, and that's aqueous, goes to zinc sulfate, which is zinc ion aqueous plus again the sulfate aqueous plus the copper in basic standard state, comes out as a precipitate. Now, notice that we have a sulfate on the reactant side, a sulfate ion on the product side. These are typically called spectator ions. They do not enter into the reaction, but are certainly required to be the counter ion to those ions which do enter into the reaction. If we remove those just so that we can see the substances that are reacting, we can construct the net ionic equation. In this format, zinc reacting with copper. Goes to zinc. Plus copper in basic standard state. So there's your net ionic equation. Next, we need to look at the oxidation reduction process and the single replacement reactions. You recall that oxidation refers to loss of electrons or giving up electrons by one species in the reaction, and reduction is the gain of electrons by one or more of the species in the reaction. Now, looking at this, we can see, using the ionic equation, the oxidation states of zinc on the reactant side is 0, it's in basic standard state. Copper is +2, copper 2 ion, zinc +2 ion, and copper in basic standard state is 0. If we compare the oxidation state of zinc on the reactant side to the oxidation state of zinc on the product side, we see it's gone from a 0 to a +2 oxidation state. In order to generate a more positive condition, the zinc has to give up 2 electrons, so we generally refer to that as lost 2 electrons, like this. On the copper, we don't really lose electrons, because copper will find them, if you will. So we start at +2 oxidation state and finish at a 0 oxidation state. So in order to neutralize the 2 positive charges, copper will gain the 2 lost electrons and form the copper in basic standard state. Of course, we have in here a balance of charge as well as a balance of mass, so conform to the law of conservation of mass and conservation of charge and the oxidation. So we say one element of zinc losing 2 electrons transfers the 2 electrons to 1 ion of copper, copper 2, and forms a basic standard state right here. The processes can be shown in half reaction form. If you take zinc, basic standard state, you can show it to be changed to zinc ion, aqueous, plus 2 electrons. So this shows the nature of this as a giving up electrons. You're putting the electrons on the product side, and so this is the oxidation process. Now, another term that's used in oxidation reduction processes is oxidizing and reducing agents. If zinc is undergoing oxidation, then it's going to be called reducing agent. That is, it's causing something else to gain the electrons that it is losing. If we look at copper in a half reaction format, we can see copper, aqueous solution, will be gaining the 2 electrons delivered by zinc to produce the basic standard state form of copper. As the copper 2 gains electrons, this is the reduction process. And with this, then we can call the copper 2 the oxidizing agent, because it will cause something else to undergo oxidation or lose electrons, like the zinc is losing 2 electrons for the copper to achieve basic standard state. Okay, finally, in this note, the reaction conforms to the law of conservation of matter or mass and conservation of charge. The mass of the reactants certainly must equal the mass of the products, and the number of electrons undergoing from the oxidation process must equal the number of electrons involved in the reduction process. Okay, now let's look at an example of a single replacement reaction that you might see on an exam or quiz. Here's copper and silver nitrate, and copper solid in its basic standard state is placed in the presence of a solution of silver nitrate in aqueous solution. We need to write the molecular equation, the ionic equation, and the net ionic equation. Then show the oxidation reduction process in terms of half reactions of the oxidation and reducing agents. Now, in order to do this, we'll need, of course, the activity series you see here. And in scanning through this, we look for copper, which is right here, and silver, which is here below copper. So in fact, the copper will replace silver, and that copper is a more active metal than is the silver. So we can write the molecular equation as follows. So we can take copper and replace the silver, starting with copper in its basic standard state plus silver nitrate in aqueous solution. We will form the copper nitrate in aqueous solution. Now, copper 2 would require 2 nitrates minus 1 in aqueous solution. And the silver is converted to basic standard state as shown here. And since we have 2 nitrates on the product side, we will need, of course, 2 nitrates on the reactant side. And so 2 silvers would then require 2 moles of silver on the product side. From this, you can write the ionic equation in the following way. We ionize the silver nitrate and the copper nitrate and show them in ionic form. You would write it as copper, basic standard state, plus 2 silver ions in solution, plus 2 nitrate ions in solution. Then that will yield a solution of copper ions, copper 2 ions in aqueous solution, 2 nitrate aqueous, along with the 2 moles of silver in basic standard state. Now, to write the net ionic equation, we remove the spectator ions, 2 nitrates on the reactor side, 2 nitrates on the product side, and list only those items in the reaction that actually undergo reaction or change or process. So we'll start with copper in standard state plus 2 silvers aqueous, plus going to copper 2 in solution plus 2 silver, 2 moles of silver in basic standard state. So this shows all of the equations that meet this question: molecular, ionic, and your net ionic equation. Now we need to show the oxidation reduction process in terms of half reactions of each one. So to use show how the oxidation reduction process takes place in terms of half reactions, We want to show how copper goes to copper 2 ions by oxidation process, and how the silver goes to the standard state silver when the silver ion gains electrons. So we start with copper here as a solid standard state, and in the chemical process undergoes oxidation to copper 2 in solution, shown here. Then we indicate 2 electrons on the product side to emphasize that this is certainly an oxidation or loss of 2 electrons. The copper would then be called a reducing agent, causing the silver to undergo reduction, and that can be shown in half reaction in the following way. Silver ion, aqueous solution, certainly would gain an electron to become basic standard state, but in order to maintain a balance of charge as well as mass, we need 2 moles of silver ions and 2 moles of electrons, producing 2 moles of silver in basic standard state. So the 2 electrons are shown on the reactant side with the ion, indicating that the 2 moles of silver are gaining 2 moles of electrons by the process of reduction. Now keep in mind that these are processes, but the terms oxidizing agent and reducing agent refer to the individual species on the reactant side. Oxidation process would mean copper is a reducing agent. So we'll say copper reducing agent. And then silver, in the process of gaining electrons undergoing reduction, is referred to as an oxidizing agent. Okay, next we want to look at how the halogens function in single replacement reactions. First, we need to look at the activity series for the halogens, and if you look in many references, you'll see how chlorine is on top and most active, replacing fluorine and bromine and iodine. So I'm going to make that notation here just for reference, that Cl2 is more active than fluorine, more active than bromine, which is more active than the iodine as far as the activity series goes. So let's take a look at this reaction, and Cl2, chlorine, basic standard state, is the gas being bubbled through a solution, aqueous solution, potassium bromide in aqueous solution to produce potassium chloride, also an aqueous solution on the product side, plus the basic standard state of bromine, now in liquid form. Now as you look at this, you can see how chlorine replaces the bromide, forming chloride, and bromide converting into bromine, the basic standard state. Now this is of course the molecular equation. The ionic equation would show the potassium bromide and potassium chloride as ions like this: Cl2 in gas, basic standard state, plus 2 potassiums, aqueous form, plus 2 bromides, aqueous, goes to 2 potassiums, aqueous, plus 2 chlorides, aqueous, and bromine in basic standard state. Like that. Now looking at the reactant side and the product side, we find that potassium is the spectator ion in this process. So by rewriting the reaction without potassium, we have the net ionic equation. Without potassium, we wanted to go straight to bromide, an aqueous solution, which produces, of course, the two chlorides, an aqueous, plus bromine in basic standard state. Now, when we compare the chlorine to the chloride over here, what we see is that the chlorine has undergone a reduction process, where the bromide undergoes the oxidation process and loses electrons to the chlorine to chloride elements. So let's start with oxidation. So we take the two bromides in aqueous solution, going to form bromine, basic standard state, neutral, plus two electrons, and this is oxidation of reducing agent. Which is, of course, bromide in aqueous solution. Right there. Then we look at the chlorine in this process. We find chlorine undergoes the reduction. We'll put that down here as a gas, basic standard state, undergoes a gain of two electrons that were, of course, delivered by the bromide to bromine. And this goes to two chlorides, and that will certainly be in aqueous solution. So this shows the process of reduction of oxidizing agent Cl2 in basic standard state. Okay, next we need to look at the double replacement reactions. Which are also known as metathesis. Reaction. This we will do in our next class.